Okay, everybody, we saw in a previous video that the following integral, right, we called this the flux integral of a vector field, and we showed that it was equal to the following line integral on this side, where the vector field is given by the expression f of xy, g of x and y, right? We said, let this be the velocity field for a moving fluid, okay? The net amount of fluid crossing into and out of the curve was this quantity right here. Okay. And what we're saying is to evaluate this line integral, we can simply evaluate the following, the second line integral, if you will. And we put it in parametric form, and those are mostly like our homework problems, to be sure. Okay. Interesting thing, though, gang, is this. If you apply Green's theorem to the right-hand side, then you're going to get the following expression or integral. Right, Green's theorem says that you take the coefficient, for lack of better words, the coefficient of the dy with respect to x, and of dx minus that with respect to y. This is going to wind up being a positive. Like that. And this expression in the square parentheses is sometimes referred to as the divergence of the vector field. Okay, the divergence of the vector, sometimes the two-dimensional divergence of the vector field. And when we think of the word divergence, we think of moving away from, right? So how does this, what's the divergence of the vector field and the sum of all of that? What's that got to do with the outward flux of F across C? Well, we'd like to see if we can draw some parallels between these things and explain the physical interpretation of what's going on here. Okay, and before I actually do that, let me remind you of something that we all did in our Calculus 1 and Calculus 2 days. Okay, so this is kind of like a quick little reminder. Okay, so the work done by a variable force moving an object along a straight line. Okay, think of like a variable force. Well, maybe we want to stretch or compress a spring, right? And so when we did problems like that back in Calculus 1 and Calculus 2, what we did was we took an interval, right? We say from A to B. All right, and we divided it up into n tiny subintervals, right? 10 really tiny subintervals of width delta x, we'll say, right? Here's one such interval right here. And we'll call this the ith subinterval. And there are n of them throughout the interval from A to B. And the idea is to find the amount of force to move the object from this left hash mark to this right hash mark right here. Okay. Well, the next thing we did, right, when we divvied up the larger interval into subintervals, was we chose a sample number in each one of those intervals. Okay, now that sample number could be either the left endpoint or the right endpoint or the midpoint of each subinterval. And you may remember that terminology from left Riemann sums, right Riemann sums, and midterm Riemann sums. Okay. It could be any sample number in the interval, though. So I'm going to call that hash mark C sub I. Remember, again, the hash marks are very large because this is a magnification of the x-axis. And our question is, how much does the force vary over such a tiny interval? Yeah, not much, huh? In fact, I would say that the force, and I think you would agree, over such a small subinterval is approximately constant. To be a little bit more technical, the force over that interval is approximately equal to the value of the force at either the left endpoint or the right endpoint, or any number in between, we'll say the sampling number. And then, of course, the next thing after that was it led to a Riemann sum and so on. Right here, the force would be, we would think of the force over such a tiny distance as approximately force times distance. And so the amount of work over such a tiny subinterval we'll call W sub I for the I subinterval, is approximately equal to this quantity. Okay? All right, and so I'm going to be using this idea of sampling point in our next consideration. All right, now let me show you a quick visual. Okay, I'm going to share my screen here. Let me find the right one. There we go. When we think of the outward flux of a vector field across a curve, here's a nice visual right here. Here the curve happens to be ellipse, but that doesn't matter, right? It could be any curve. Notice that the vector fields coming out of the curve are longer than the ones going in, so we calculate the net amount of fluid crossing into and out of the curve, and of course that was the quantity of the line integral. Okay. What we want to do is we want to imagine a small rectangle being dropped inside. Okay, a small rectangle being dropped inside. That might look something like this. Okay, so imagine that field of arrows you see there. That's the velocity field. And we want to drop a tiny rectangle into that field. Now, of course, you see a large rectangle, right? But we imagine that the sides are very, very small. Okay. And one other thing I want to show you about the smallness of the sides of those rectangles and where the recall of the Riemann sum was coming from. Okay, take a look at this. Now, look at that line segment and look at the arrow. So I have some of the field arrows are actually touching the curve itself. All right. Watch what happens when I shrink the curve. Okay, see that? Now, mind you, gang, before I continue, notice that the vectors are all of varying length and directions, right? So that we have a varying force over that little tiny line segment. But what can you say about the arrows as the line segment shrinks? Look at this. What do you notice about the arrows? Yeah, that's right. The more the line segment shrinks, the less the arrows vary. In fact, they all start looking like each other. Our variable force starts to look like a constant force the smaller the subinterval gets. Keep that in mind when we take a look at the rectangle that we're going to drop inside of our fluid. Okay, so that's going to look something like this. Let's make another picture. Here's our very tiny rectangle, which is greatly magnified. Okay. I'm going to label this corner right here, XY. This corner, I'll label it as X plus delta XY. All right. This corner up here, we'll call this X plus delta X, Y plus delta Y. Of course, this one over here, we'll call this one X, Y plus delta Y. Okay. Again, what I want to do is this. I want to examine this quantity right here. See these three? I want to examine this quantity. Actually, said another way, I want to apply that expression to all four sides of this rectangle. Okay? Now, in order to do that, I need three things. The field, a unit normal vector to the curve, and a length. That's what all three of these are, right? The field, a unit normal to the curve, and a length. Okay. Well, how about this? Along this horizontal curve, or this horizontal line, I'm going to use the unit normal vector, shall we say negative j, and the length of it will be delta x. Okay. Along this side, I will use I for my unit normal vector, and the length of this side will be delta y. Along this side, positive j. And along this side, negative I. okay? So I've got a unit normal vector to all four pieces of the curve, my rectangle. I've got the length of each piece of the curve, okay? And remember, again, this is a really, really tiny element. We're just magnifying it so we can see it better. What I don't have is the field yet. All right, so let's do this. Let's make notes to ourselves that along this horizontal line, the bottom of the rectangle, okay? Remember, gang, this line segment is so small that the force varies very little over such a small line segment rather, okay? In fact, the force is approximately the same at every single point within the line segment, including the ends of the line segment. Think of that Riemann sum that we were working on, right? Remember that? Here, look, real quick. Remember, the variable force was approximately constant over such a tiny interval, so that the force was approximately the same as the value of the force at the left end, the right end, or any point in between. Okay, I'm using exactly that concept, gang, here. I'm going to say that along this curve, and I'm going to call it C1, I'm going to evaluate my force at the left end of the interval, xy. Okay, I'm going to evaluate my force at the left end. The value of the force is essentially the same at every point along this horizontal line. I choose the left end. Okay. Now along this side, I'm going to call that C2. I choose to evaluate my force at the point x plus delta xy, the lower corner. I could have chosen any point along this vertical line. I could have chosen, again, I could have chosen this point right up here. Yeah, I could have chosen that one. Okay, but I'm choosing how I want to evaluate my vector field because I've got a particular goal in mind. Okay, so just keep that in mind too. All right, I've got something in mind. All right, along this horizontal line, I'll call it C3. I want to evaluate my force at the left end, not the right end, not any point in between, but specifically at that end. Okay, and finally, along this curve, we'll call it C4. I want to evaluate my vector field. I can use any point along this vertical line I want. I choose to use the lower corner, xy. All right, that's my setup. All right. All right, now, for C1, the expression f dotted with n ds becomes. Okay, and that is equal to. Okay, so far so good. Now I'm going to go along C3. I'm going to go out of order. F dotted with n ds becomes. Okay, now again, remember, let me move this down a little bit. Along the top or horizontal line, I'm going to evaluate my vector field at the left corner, x, y plus delta y. And when I dot these vectors together, that. All right, how's that look? Okay, now I'm going to go across C2. And when I do, F dotted with N ds becomes, okay, now remember, gang, along C2, we're going to evaluate our vector field at this bottom corner, x plus delta xy. Okay, to get this expression. And finally, we're going to go along C4, right? Remember, along C4, we're going to evaluate our vector field at this corner. Instead of anywhere in between, I chose this corner right here. Remember, there's a reason I chose these points. There's a bigger picture at the end. Or not at the end, but it's coming soon. All right, so for C4, okay, how's that look? Now, the next thing I'm going to do, of course, you probably figured this already, is I'm going to add up all four of those quantities to get the total flux of the vector field across all four sides of the rectangle. Okay, so let's say the total flux of F across the rectangle is equal to the flux across each of the four sides. And gang, I'm just going to add up all four of those quantities. All right, here they all are right here. Okay, there's this one. All right, across C1, C3, C2, C4. Add all four of them together. And here's what we're going to get. And I'm going to take the liberty of factoring out common factors, delta y and delta x. Okay. Next, I'm going to divide both sides by delta x and delta y, the area of the rectangle itself. Okay, I'm dividing both sides, again, by the area of the rectangle itself. This we can think of as the total flux per unit of area. Okay, so it's a rate, the total flux per unit of area. Okay, now here, notice after careful canceling of common factors, we're going to get the following. Oops, this should be a y, shouldn't it? My mistake. This should be an x. I'm getting a little sloppy. And hopefully, gangs, I bet a bunch of you, if not all of you, recognize these express. Do you recognize those? Yeah, yeah. It's the difference quotient, right? It's the difference quotient. Now do this. Do this. Let delta x and delta y approach zero. And as those two quantities approach zero, these two quantities approach the following, right? The very definition of the partial derivatives of f with respect to x and g with respect to y, right? So we can think of, oh, and here's something else, gang. Since delta x and delta y are approaching zero, take a look at our figure here, right? As delta x and delta y are shrinking to zero, we imagine that these three corners are collapsing in on that one point right there. And so we think of that then, this quantity, as the flux per unit of area at the point xy. Okay, the flux per unit of area at the point xy. So when you take a look at our integral again, right, Green's form, the flux form of Green's theorem, that would look like this. Okay, right, and that's exactly the integrand that we have in the flux form of Green's theorem, right? So that expression right there, that's the flux per unit area at each point in the region R. This, of course, right here, this is area, right? That's a differential element of area right there. All right, so flux per unit of area at each point. What points? The points within R, okay? And of course, the double integral says sum all that up. Okay, that's what it's saying, gang. So the integral says to sum up the outward flux at each point of the region R. Okay. The left-hand side, well, we knew what that was from a previous video, right? This is the outward flux of the vector field across C. All right, so the sum of the outward flux at each point within the region R is equal to the same as the outward flux of the vector field across the curve C, which bounds the region R. So again, think of a figure that looks something like this. Okay, so here's our curve C, right? And we imagine that it's inside of a velocity field for a moving fluid, all right? Here are some points within the region R, which is bounded by C, okay? And so you might have something like this, right? We imagine fluid coming into and out of these little points within the region R. Okay, what's the net amount of fluid, right? What is the outward flux from point to point within the region R? Well, there's an infinite amount of those points, right? So what we do is we sum them all up with an integral. Okay, so the net amount of fluid that's moving into and out of those points within the curve is equal to the net amount that's crossing the curve. And that's what Green's theorem tells us in the flux form. Okay. I know it was a rather lengthy discussion there, gang, but hopefully you get a greater appreciation as to what this expression means and how the two are related with Green's theorem.